All right, welcome to our live solutions. Um, Good morning, good afternoon, good evening, good night, depending on the time of the day that you're seeing this. Um, let's just jump right into it. Um, a student investigated how the potential difference across a filament lamp affects the current in the lamp. Figure 1 shows the circuit the student used. So you have this the variable resistor, the lamp, the ammeter, the voltmeter. All right, just for the sake of emphasis, this particular question is strictly for foundation. So if you're doing higher, then you have to seek out other videos that we have on ground. Um, Figure 2 shows a circuit symbol. Here we have figure 1, we have figure 2. Then it says, what component does this symbol represent? So that's straight up, that's a battery. Which component from figure 1? This is figure 1. Yeah, that's figure 1. Which component from figure 1 did the student use to adjust the potential difference across the lamp? And that's a variable resistor. 1.3 says when the voltmeter was not connected to the circuit, it gave a reading of 0.4 volts. How can the student correct the readings taken from the voltmeter? That's, zero error. You just subtract 0.4 from each reading. 1.4 says the student recorded three values of current for each potential difference. Table 1 shows the results for 2.5 volts. Calculate the mean current in the lamp. You know, the mean is just, um, let's say, mean is I1 plus I2 plus I3 divided by 3. All right, so that is 0.54 plus 0.58 plus 0.53. Divide all of that by 3, and that gives 0.55 amps. That gives 0.55 amps. All right, and let's move on to the second question. Is that, 1.5? Okay, we've got 1.5 right here. Calculate the power of the lamp when the potential difference across the lamp was 4.8 volts. The current in the lamp was 0.75 amps. We get the power. You know, power is potential difference times current, and that's 4.8 times 0.75, and that is 3.6. Power is measured in watts. So you should keep that in mind. 1.6 says you should calculate the resistance. You should calculate the resistance of the lamp when the potential difference across the lamp was 4.8. And guys, for each of those questions, to see how well you prepared, you can, as well, pause the live stream, quickly solve and play and see if our answers match. And if not, you make corrections when necessary. Practice makes perfect, and that's how it works. All right, so 1.6, you're asked to calculate the resistance of the lamp when the potential difference across the lamp was 4.8 volts. You have the current, so you have I, and then you've got V. What you need R, um, V equals IR, and R equals V over I. If you rearrange that equation, that will be 4.8 volts over 0.75 amps. That should give you 6.4 ohms. Going to 1.7, complete the sentence. Choose answers from the box. Each answer may be used once, more than once, or not at all. That's interesting. Increasing the current, in a filament lamp makes the temperature of the lamp. What do you say? Increase, definitely. And the resistance, here, just for knowledge purposes, aha, with a T. So once the current increases, the thermal energy, this is thermal energy or heat, that's what I want to call it, and this is your current. They're directly proportional. Increase one, the other will increase. And the resistance of the lamp, you can see the resistance too. Resistance is directly proportional to the heat. Increases as well. We're going to 1.8. Which graph shows the relationship between potential difference and current for a filament lamp? Oh, interesting. Okay, so filament lamp, that's the first one. Okay, we're going to question T. Figure 3 shows a lift near the bottom of a building. The lift is attached by a cable to a counterweight. An electric motor moves the lift. The lift is moving up. Okay, let me just zoom out so you can have a full picture. As the lift moves up, how far does the counterweight move down? Oh, the same distance. The same distance. The same distance. 2.2 says, what happens to the gravitational potential energy of the counterweight as it moves down? The gravitational potential energy decreases, a decrease in height. Calculate the change in GPE when it moves up for, let's say, height. You can give him the equation here. So, you have the mass, 1,300. You have G, that's 9.8. And then you have height. What's our height? 4. If you plug this into your calculator, you have 50,960 joules. Since the unit is in joules, you just leave it that way. No need to change it. Complete the sentences. Friction between the brakes and the cable causes the speed of the lift to decrease. As the speed decreases, there is a decrease in the kinetic. You should know that. Motion and kinetic. As the speed decreases, there is an increase in the internal, that's the total energy. The model transfers different amounts of energy each time people use the lift. Which factors affect the amount of energy transferred by the model as the lift moves? Tick two boxes. All right. And that's the distance moved by the lift. And then the weight of the people in the lift. 2.6. The weight of the lift and the counterweight stretch the cable by this guy. And that's your extension. And this guy is the spring constant. Well, again, yeah, that's all. You get your EPE, and that's 0.5 times 880,000 times 0.015. Plug this into your calculator, you have 99 joules. A lift system using a counterweight is more efficient than a leaf system that does not use a counterweight. How does having a more efficient system affect the energy transferred by the model? That's um, when it comes to energy efficiency, you reduce wastage. Less energy is transferred. A teacher demonstrates. We're on to question 3 now. A teacher demonstrated that the radioactive isotope americium-241 meets alpha particles. You have the figure 4. An americium-241 nucleus emits an alpha particle and turns into a neptunium nucleus. Which is the correct nuclear equation for this decay? Oh, this is an alpha. Let's see. Wait. Okay. Let's see what we're doing here. A correct one, a decrease by 4. So this is an alpha decay. The first one will work. And then going on to alpha decay, a decrease by atomic mass 4. You have that, and then an increase, a decrease in the atomic number. That's 2. If you check the others, it doesn't conform to that principle. So first one goes. 3.2 says, what is the furthest distance that alpha radiation can travel in air? Okay, sorry guys. What is the furthest distance that alpha radiation can travel in air? That's just a few centimeters. That's between 6 to 8 centimeters. That's the highest. All right, some materials will put the upper range as 10, and some will just say a few centimeters. And that's just for you right there. The teacher placed a piece of paper between the American 241 and the radiation detector. The reading on the count rate meters decreased by a large amount. Why does the decreased reading show that American 241 emits alpha radiation? Take one box. Well, if paper, I mean, when it comes to the penetration power, paper will stop, a sheet of paper will stop alpha, aluminium, 5 millimeters of aluminium will stop beta, and then gamma will be stopped by a few centimeters thick um, of lead or concrete. So here, paper stops alpha radiation. All right, now the teacher replaced the americium with a source of beta radiation. Which symbol represents beta? That's definitely the first one. You have this or this. Aha. 3.5, the count rate from the source was 119 plus or minus 7 counts per second. Calculate the smallest count rate this could have been. And that's 119 minus 7. You know, this means lower range 119 minus 7, upper range 119 plus 7. So 119 minus 7, this gives 112 counts per second. 3.6. A teacher investigated how the distance between a different radioactive source and the detector affects the count rate. Draw one line from each type of variable to the description. So here we have our what we need to keep the same. Let's start from there. We need to keep our radiation and radioactive source to keep it the same. That's one. Let me zoom this out. And what we need to change from time to time, that's the distance between the source and detector, and what we're trying to measure, the count rate. We have no business with the time at this moment. All right. Figure 5 shows how the count rate from the different radioactive source changed with the distance from the source. It says we should describe the relationship between distance, let's run, from the source and the count rate of rise. Now let's just take 2 points. Let's take point 60. At point 60, we'll have a distance of let's say roughly 5, roughly. And then let's say at a distance of 20, we'll have a count rate of, so here we'll have a count rate of 60. At a distance of 20, we'll have a count rate of 5. So here we'll have a decrease as the distance increases. So that will give you your conclusion. As the distance increases, the count rate decreases. Easy peasy. So as the distance increases, the count rate decreases. All right, and just give an example here. Let's see. You can give the first example that between 5 and 20. Okay, let's just put that between 5 cm and 20 cm. Count rate decreases from 60 to 5. Yeah, that's it. Or you can pick any 2 points. You still get your full marks. Number 4 says figure 6 shows a swimmer wearing a wetsuit. The wetsuit helps to keep the swimmer warm. A student wrapped a thermometer in a piece of wetsuit material and placed the thermometer in water containing ice. Figure 7 shows the apparatus. You can see all of that. Thermometer, beaker, blah, 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 vd, blah. Let's see what exactly the question is asking us to do. After 30 seconds, that's your time. In the water, the temperature of the thermometer had decreased by 7.5. That's the change in temperature. Calculate the average decrease in temperature. So average decrease in temperature Some might prefer to have it as T. Either way, you still be right. Is the sorry about that. That will be 7.5 degrees Celsius over the time. That's 30 seconds. This will give you 0.25 degrees Celsius. That's the average. Okay, the student recorded the temperature of the thermometer after 30 seconds for 4 materials. Each piece of material was the same size and thickness. In each test, the starting temperature of the thermometer was 21 degrees Celsius. You have the readings. Then it says complete figure eight using the data in table 2. Okay, what's missing here? Y and Z. Y is 16. Y is 16. Let's make sure that we're okay. It might not be perfect, but let's just get the idea. Okay, and then the second bar, Z, that's jumped to 12. 12 is just E. Okay, that's rough, but still fine. Which material is the best thermal insulator? No, the best. Wait, there is something missing here. Oh yes, this guy. We need to put. Oh, all right. We need to put degrees Celsius right there. Now this question is asking us which material is the best thermal insulator. Now, the best thermal insulator will have the smallest change in temperature. Right. The best thermal, all right, have the smallest change in temperature. So W has 13, X has 8, Y has 16, and Z, okay, Z has 12. Now, when you do your math, starting temperature is 21. All right, starting temperature is 21, and this is the final. You see what we're building now? This is the final. All right, so for the first one, you do initial. Well, since the initial temperature is more than, so you do 21 minus 13.5. That gives 7.5. That's what we'll have for W. X, we have 21 minus 8. That gives that gives 13. Y, 21 minus 16. That gives we'll have 5 for our guy here, and then 21 minus 12. That gives, sorry, that gives 9. Now, this guy has the smallest change in temperature. So an insulator will make it difficult for heat and electricity to pass through it. So definitely the temperature for Y isn't changing that much. So that would be the guy with the highest um, temperature change. So that is Y. Why? Um, okay, is our answer is Y, and then we're asked why. Well, that's because it showed the smallest change in temperature. Okay, so let's talk about that. If you're confused, just prefer to pause the video, go back and see how we got our answers. The student tested a new material with a greater thermal conductivity than material Z. The piece of a new material was the same size and thickness as the piece of material Z. What was the temperature of the material after 30 seconds? That is, let's see. Do, 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 do. Okay, the material Z. After 30 seconds, definitely it will be less than 12. All right, it will be less than this guy. The temperature will continue to drop. 4.6. During the investigation, 0.0150 kilograms of ice melted. The temperature of the water and ice did not change. Okay, we got the mass. Good. Temperature did not change. Hmm, interesting. That is latent heat. All right. Um, for specific heat capacity, that's talking about um, the temperature needed or the energy. Yeah, that's the word. The energy needed to raise the temperature of 1 kg of a substance by 1 degree Celsius. All right, and then latent heat is talking about the energy needed to change the physical state. The energy needed to change the physical state of a particular um, substance. 1 gram, 1 kilograms rather, not 1 gram, 1 kilograms of that substance. You can check your um, notes for um, confirmation. And that's the definition which you need to know and master. Very important. You should be able to differentiate between the two. All right, so um, energy. We've been given the equation here, so no need to worry. This is L. This is L. That's not 0.0150 kg multiplied by 334,000 joules per kilograms. Punch this into your calculator, you have 5,010 joules. Oh, the unit is there. No need to worry. The student wanted to determine the density of a wetsuit material. The student measured the length of one side of a cube of wetsuit material with a micrometer and a ruler. Table 3 shows the results. Interesting. I have the results here. Choose the answer from the box. The results show that compared to the ruler, the micrometer has a higher resolution. Resolution. Yeah, resolution. By now, you should know what resolution means. All right, that's the smallest or the lowest accurate and precise measurement you can get on um, an instrument. All right. Write down the equation that links. Oh, there should be a walkover for you. Okay. 4.8 says the student calculated the volume to be this, the density is this. Get the mass. The density equals mass over volume. Mass will be density times volume. Yeah. So that is 0.3, not. You might decide to remove you know, that that's 0.186. Plug this into your calculator. You should have 0.0558 grams. And then number 5, let me bring this out, says figure 9 shows some of the energy resources used to meet the demand for electrical power in the UK on one day in 2020. Interesting. Hmm, this is revealing. Okay, you have that for 5,000, 10,000. You have wind, you have coal. You can see what coal is and the amount of energy coal can give. In gigawatts, you have wind, and then you can see the demand. So look at the supply. So you can say here you've got the supply as against the demand. All right, let's see what the question is saying. The maximum demand for electrical power on that day was at 6 p.m. Yeah, let's got this point. What's it saying? Determine the percentage of maximum demand for electrical power that was generated using gas. So very simple. The stuff you have here, you have 30,000. You have 30,000 here. That's the maximum demand you have. That is okay. Let's just put that down. 30,000 gigawatts. All right, and then let's check what gas can give us. Gas can only give us at that point 6 p.m. Remember, this is 6 p.m. Let's save this. 6 p.m. A gas can only give us, let's say, about 16,500 gigawatts. So, do your percentage thingy, 16,500 over the demand, 30,000, and do your multiplied by 100. Plug this into your calculator, you get 55%. They have 55%. All right. 5.2 says the UK government wants to reduce carbon emissions as much as possible. Um, which energy resources need to be used less to achieve this? To reduce carbon emissions, you have to reduce the non-renewable energy resources, and that's coal and gas. 5.3, what is this network called? What network? That's a network of transformers and transmission cables. You know what that is? That's national grid, the national grid. And one little piece of information you should note that the national grid does not include the power station and the consumers. Aha, in case you come across similar questions. Power station and consumers, I mean homes, are not part of the national grid. National grid is just a system of transformers and transmission cables. 5.4 explain how using stable transformers makes the network efficient. We're transforming, I mean, did I say transforming? We're transmitting electricity at the same power, all right, but at a higher voltage and a lower current for efficiency. All right. Now, the lower the currents, the lower the energy loss. Aha. And if you decide to transmit at higher currents, you have a lot of energy losses and of inefficiencies, which could be very, very, very costly to the government and to the generation company. So no one wants to be in that kind of situation. So why not just use you know an easier approach? So here you can say um, step-up transformers makes the network efficient by increasing the potential difference while current is reduced. So there is a lower energy loss to the surroundings, or you can say energy dissipation to the surroundings. All right, you know what I mean. Um, what else? What else? What else? Number six. A student made measurements to determine the specific heat capacity of vegetable oil. Figure 10 shows the equipment the student um, actually used. You have the joule meter, you have the electric heater, beaker, top pan. What else have you got? You have thermometer, and you need to describe how the student could use the equipment shown in Figure 10 to determine the specific heat capacity of vegetable oil. That's nice. I love vegetable oils, you know. They're good. And they smell nice. All right, so let's come back. Let's come back. All right, so what are we measuring? This is our dependent variable. Uh-huh. And then one thing, yes, whenever you're writing or describing the methodology of an experiment, make sure, very, very important, very, very important, that you include at least one control variable. At least one control variable, something that you keep the same. Yeah. And then you have to be very detailed too. Have to be very detailed. Just imagine yourself writing a manual. You're writing a manual for somebody, maybe the person that hasn't performed that experiment before, and then you're hired to write a manual. And your manual should be logically arranged and coherent, in a manner that if someone that has no idea of how to do it picks up your description of that experiment and follows it to the letter, simple language, don't complicate things. The person should get the same result you got. So don't complicate things. All right, so let's um first thing you do, you measure mass vegetable oil using the top hand malins. You've been given the equipments here, so you have nothing really to um, worry about in that regard. But for hire, um, for those doing hire, you won't be given the equipment. So you have to plug that in yourself. All right. Measure mass of vegetable oil using the top pan balance and also measure the start temperature of the oil using the thermometer. Um, remember to use your connectors. Then place the beaker of oil on the heater. Remember to switch it on. All right, switch it on to heat the oil. You measure the final temperature of oil using the thermometer, okay, and measure. Um, okay, I think this will be much better. Then measure the energy transferred using a joule meter. Finally, calculate the increase in temperature. That's your theta, or all right. You don't need to write the two. I just wrote the two here. Um, just for you guys in exam situations, you don't need to write the two. Just one will be fine. Anyone is still saying the same thing. Um, and you use the equation. And what's the equation? That's your energy, thermal energy. Okay, let me write it in full. Thermal energy equals mass times specific heat capacity times what are you again? Change in temperature. All right, that's your E equals MC change in theta. Yep. So you've gotten what you need, and you move on from there. Give one risk when using the equipment in Figure 10. Electric heater. Don't burn yourself. Burns, yeah. Or you can have cuts if the glass breaks. You can have cuts. All right. So a different student did not have a joule meter and calculated the energy transferred by the electric heater. Write down the equation linking energy transferred, power, and time. All right, you're asked to use the physics equation sheet. All right, you can use that. And then for those that um, are familiar with this equation, you know, if you've, that's why you need to practice a lot of questions. The more you practice questions, the more you become really familiar with the with the equations. All right, so we have energy. Okay, let's make power the subject. So that is power equals energy transferred. We're almost coming to the end. Um, Energy transferred over time. So that, well, that's fine. That's fine. Um, 6.4 says the electric heater had a power output of 50 watts. Good. That's your P. Remember to list your variables. Calculate the time taken for the electric element to transfer 4,750 joules. That's 4750 joules. That's your energy transferred. All right. You need the time. That's T. Okay. Interesting. Power equals energy over time. That is, what's power? Power is 50. Okay, let's do it this way. I would love to rearrange my equation, all right, before plugging in the values. What are we looking for? We need the time. Time here, you know, time here will be power. No, not that. Time will be energy over power. Yes. This would be energy is 4,750, and then power is 50. Plug this, you get 95 seconds. All right. In a deep fryer, vegetable oil is heated by an electric heating element. Food is then cooked in the hot vegetable oil. The deep fry contains an electrical component to monitor the temperature of the vegetable oil. Figure 11 shows let's zoom out, shows how the resistance of this electrical component changes with temperature. Hmm, interesting. We've got resistance here, and then we've got temp. Oh, that's bad. We've got resistance, and then we have temperature. Interesting. What electrical component is used to monitor the temperature of the vegetable oil? A thermistor, depends on the temperature to control the resistance. So, revise your electrical components. All right, so we have 6.6. All right. The electric heating element in the deep fry automatically switches off when the vegetable oil reaches a certain temperature. Figure 12 shows how the temperature of the vegetable oil changed after the deep fry was switched on. So we have all of this now. Okay. Determine the resistance of the electrical component when the electric heating element automatically switched off. Hmm. Interesting. Interesting. So we're told to use figure 11 and figure 12. Figure 11, where are you? This is figure 11. And figure 12, this is you to determine the resistance. Okay, what do we have here? Um, we have the temperature, and then we've got the uh, resistance. Okay. So when you switch off the resistance, okay, let's see what we've got here. Okay, so when the electric heating element automatically switched off, your resistance will be that'll be about 250. Yeah, that will be about 250 from what we have here. And then question 6, some chips were put in the deep fryer. All right, in the deep fryer, water in the chips underwent a physical change and became steam. Why is this a physical change? Hmm. All right, now the water will recover its original properties if the steam is cold. Yeah, because it's a physical change. And for physical changes, yeah, one thing that separates physical changes from chemical changes is that physical changes are reversible or reversibility. Chemical changes aren't reversible. Yeah, I think, yeah. I don't want to make this video too long. Yeah, I think that's all. If you've got any questions, drop it in the comment section. And I'll see you guys very soon.